a simplified presentation of Bloch's theorem, say in one dimension. So we do it in one dimension. Okay. And in one dimension, the solid state Hamiltonian, which is non-interacting, I believe, is given by the following. Okay. The Hamiltonian is given by h of x is minus h cross squared by 2m d squared by dx squared plus v of x. Okay, so the electron sees the potential Vx. What is V of x? V of x will look something like this. Etc. Okay. So say this is the zeroth side, this is the first side, this is the second side. So the electron Hamiltonian is periodically attractive. Okay. Because maybe there is a nucleus, there is an electron, and the electron is zooming past in one dimension. So it keeps seeing an attractive potential, and this is a caricature of a genuine Coulombic potential. So this is something what I would call as a model Hamiltonian. Model representation, the idea is that the Hamiltonian has to be periodic. So we basically have over here that V of x plus A is equal to V of x. What is A? A is this distance. Therefore, h of x plus A is equal to h of x. What is the problem I am seeking to solve? Given the Hamiltonian, that is given this potential, whatever it is, as long as it is periodic, the wave function will be equal to E, let me call it epsilon psi x. What is the quantum mechanical problem? You must know the psi and you must know the epsilon, or the eigenvalue E, or the energy E. Okay? So you must know both of these. Okay? And here is a potential which is not that simple. It goes on and on. And for this potential, how will you solve the solid state problem? So the answer is the following. Unless you give me that potential, I cannot solve it. Okay? But if you give me certain properties of that potential and the Hamiltonian, I can say certain general things about the Hamiltonian and about the wave function and about the energy. And what I will say, and I will prove this for you, that psi of x is characterized by a quantum number k. What is this quantum number k? Since there is something periodic, since there is a symmetry, there is a quantum number associated with the wave function, which I will call k, and therefore the energy is characterized by k. What is this mystical k? We will come to it in a minute. Okay. At the end of this lecture, psi of k of x is such that psi k x plus a is equal to e raised to I Ka. Okay. The Hamiltonian is periodic. The wave function is not periodic. The wave function picks up a phase factor of Ka as soon as you traverse by a distance a, where a is the lattice constant. This is the statement of Bloch's theorem. Given a periodic Hamiltonian, you will get the wave function which has this one property. And this statement is in one dimension is a statement of what is now known as the Bloch theorem. Bloch was a mathematician around, I think, the late 1800s, maybe early 1900s, who proved the general property of differential equations which have this kind of property. So let us proceed and see what it is, how to proceed and prove this rather important statement. So the proof proceeds in a number of ways. You define a translation operator which I will call T. Okay, it is characterized by some translation A or something. So the translation operator, and I will prove at least 4 properties of this translation operator. So the translation operator is such that T of A acting on psi of x is equal to psi of x plus A. So in other words, it translates the wave function by a distance A. T of A, h of x is equal to h of x plus A, which, because of the symmetry of the problem, is such that it is equal to itself. The Hamiltonian is equal to itself, and that's the core, the first thing that I will go ahead and prove for you, and I will prove that the Hamiltonian and the translation operator commute. Basically have h a psi of x is equal to h of x, writing down psi of x plus a, and what the symbol means over here is a commutator, that is this operator into this operator minus this operator into this operator is equal to something. And we will show that it is 0. So when the translation operator then acts on h and psi together, I'll have h of x plus a, psi of x plus a. And since h of x plus a is equal to h of x, it is equal to 0. So the upshot is the translation and the Hamiltonian, the translation operator and the Hamiltonian operator commute, therefore they can be simultaneously diagonalized. Or in other words, if lambda is the eigenvalue of T of A, and then let me call it lambda A, you have to characterize it by something called lambda A. Okay. It is also the eigenvalue of h of x. Is part 1. This is the first step. The second is that the translation operator is unitary. T of A is unitary. How do I show this? I show that T of A is unitary very simply by saying that let T of A act on psi of x, then its complex conjugate or the Hermitian conjugate of this is psi star x T of A that. But T of A acting on psi of x means that you get psi of x plus a, that is what you get for the left hand side here. Here you, and if you were to take the complex conjugate of this, you get psi star x plus a. So please keep this in mind and we proceed. So I need to erase this part, and I'm assuming that you realize that this is quite clear to you. That is a periodicity in this problem. So I basically what I do the following. I take integral of t of psi star x t Hermitian conjugate t goes with an a if you want psi of x dx. I do this. Okay. Now what is this? If I were to look at this step and the step below it, this is equal to integral of psi star x plus a psi star x plus a dx. What is this? If the wave functions are normalized, whether it is x or x plus a, I can just translate it by making x plus a go to y, and taking dx to be equal to dy, then equal to 1 by normalization. Which means that psi star x psi x and this quantity over here, okay, this quantity over here is just equal to unity. Therefore, it means the PA dagger, PA is equal to identity, and therefore PA dagger is equal to PA inverse. The translation operator is unitary. It is another matter, although it is not important for this particular problem at hand, it's another matter to show that this is also equal to P of minus A. Okay. That comes from the definition of the translation operator. If you translate something by A, then you want to translate it by minus A, you come back to the original state. But since it is unitary, okay, then the eigenvalue must have a certain property. Okay. What is that property that it must have? So the next thing that I have to show for you is that the eigenvalue, that is the third thing, have moduli 1. That is, the eigenvalues are of an exponential type. The eigenvalue is like e raised to something. Okay. That is, I have to show that lambda A will be something like e raised to I f of a. F of a is real, but it is pure this space factor. How do I show that? That's not difficult to show. How do I show this? I take any unitary operator, okay, and operate it on some wave, on some function in the linear vector space, okay, and this is say equal to lambda n n. You don't have to have T itself. Any unitary operator will have this property of moduli 1. U of n is equal to lambda n. Therefore, I have U dagger n is equal to lambda n star n. Now patch this with this. Use this as the bra, this is the ket. What will you get? N U dagger U n is equal to lambda n modulus square n n. Take the left hand side and patch it together. Take the right hand side and patch it together. You will get the next step. If you get that step, okay, supposing n and n are normalized. So this is 1. And you know that U dagger is equal to U inverse. So again, you have 1 over here, the identity matrix. The identity matrix n n, therefore you get 1 is equal to modulus lambda n square. Proof, QED. Okay. So I've actually proved this. Now there is a fourth thing, and this is the main point. Okay. I will come to the main point right now. So we investigate this further. Take the translation operator. Take it again. Take it again and again and again, say n times. Okay, so you do this n times. Operate it on psi of x. This is equal to t the power n of a psi of x. If I were to operate this n times into psi of x, I get psi x plus a, psi x plus 2a, psi x plus whatever it is. Okay, so I basically get psi of x plus na. Right? But every time I operate, I do this. Okay, this has to be equal to e raised to I f of na psi of x. That is the left hand side. What is the right hand side? The right hand side, you take t operating on this. So you basically have e raised to I n f of a psi of x. You let it operate once, you get psi x plus a. Okay. If you get psi x plus a, that is e raised to I f a psi x, and you do it n times. Multiply it there. So essentially, what you have is e raised to I f of na is equal to I n of f. Now you use a scaling argument, and the scaling argument I can explain further, but what it means that if I were to take f of a to be proportional to a, then say let f of a be equal to some k times a, because I need one more eigenvector that is for the wave function, that is k. In that case, this step implies this and this. This is an ansatz. Okay. If I were to take this, I will have, let us say, I'll be able to satisfy this. Okay. Because in that case, f of na is equal to k times na. Okay. That is the left hand side. And the right hand side would be e raised to I n. So, I mean, you can satisfy both sides if you were to make this linear ansatz for f of a. So basically, what I have is I have a very simple form for the eigenvalue. The eigenvalue, this time eigenvalue, is nothing but I, K, A. Let me explain this step just a little bit more. What I am doing over here is not that mysterious. Supposing I give you a function, say s, L. Supposing, example. And I say this function has this property that s of 2L is equal to 4 times s of L. And then I ask you, what is s of L? So what you say, sir, there's one way to approach this problem. You make the ansatz that s of L is equal to L to the power x. And if you'll allow me to make this ansatz, then this quantity is 2 to the power x, L to the power x, 4 into L to the power x, L to the power x cancels out, therefore x is equal to log 4 by log 2, log 2, and that's equal to 2. Therefore, in this particular case, let me erase this. I have s of L is equal to some constant into L squared. What is that x? It is a square. That lo and behold, that is true for the surface say of a cube, where C1 is equal to 6. So that's how you go ahead and it's even simpler than that, because I'm saying in this particular case, that s of 2L is equal to 2 times s of L. That is what I have done. Now I believe that since I've recommended this book, Kittle, Introduction to Solid State Physics, but the quantum theory of solids, you would have at least read the first chapter or maybe a little bit of the second chapter. And I'll have to say something which is very important and said over there. So I basically have that my psi of k of x plus a is equal to e raised to I k a. Because the operator which simultaneously diagonalizes the wave function and translation operator is of the form e raised to I k a. At the eigenvalue which is e raised to I k a. Okay. Having done this, you might say, what is k? The next step, which has nothing to do with the previous step, previous 4 steps, what is k? To do this, you use something which is a belief. I mean, which is actually, it cannot be proved, but you actually do it. Okay, and you say that I'm going to use periodic boundary conditions. Since I'm in 1 dimension, I will make that 1-dimensional lattice into a circle. Okay, so say this is site number 1, this is site number 2, okay, and so on, this is site number n minus 1. Okay. That is, I have a lattice which is rolled into a circle, and I use the property that the site n is same as site. In other words, psi x plus ma is equal to psi of x. That is called periodic boundary condition. And Kittel makes a point of it. He makes it very clear in the beginning, somewhere in the chapters, first 2 chapters, that this is, it is not as though you have to accept this. Some people will say, no, let's have anti-periodic boundary conditions. He doesn't quite say it, but you can make this equal to minus psi of x. E raised to I pi. And then when you go around twice, you can make it proper psi of x. So you don't really have to do it, but most textbooks will make use of this periodic boundary condition. And if you allow that periodic boundary condition, I have that this is basically what e raised to I k ma psi of x is equal to psi x. Therefore, e raised to I k ma is equal to 1, which implies that n of a is equal to 2 pi n. Therefore, I have n n with kma. Kma is equal to 2 pi n. Therefore, k is equal to 2 pi n by m a. Right? And n goes from minus m by 2 minus plus 1, etc. 0, 1, 2. Assuming that m is even. So k essentially goes, if you go up to m by 2, k essentially goes from minus pi by a to plus pi by a. So what is my Bloch's theorem? The Bloch-Floquet theorem can now be succinctly stated by saying the following. That is to say, if the Hamiltonian is periodic, hx plus a is equal to hx, then the wave function is such that psi k of x, psi of x plus a is equal to e raised to I k a psi of x, where what is k? It goes between minus pi by a and plus pi. That is the Bloch-Floquet theorem. This is one element of it. The other element of it is if h of x plus a is equal to x, then psi of x plus a implies I k a psi of x. You can put a label k if you want. I mean, nobody will challenge you for it. And what is k? Minus pi by a to plus pi. That is the statement of the Bloch-Floquet theorem. That is the sort of proof of this Bloch-Floquet theorem.